In this video, we will learn how to find derivatives of products and quotients. We're going to start out with the product rule. This states that if you have a function that either is a product or can be written as a product, and we're going to say the product of specifically u of x times v of x. So there's two functions involving the variable x, and it can be any variable, t, x, w, y, whatever. But on here, if we have an original problem that's a product, then the derivative is found by keeping the first value in that product, so we see that there, and then multiplied by the derivative of the second value in the product, and then always adding the second function, and then multiplied by the derivative of the first function in the product. Here, the way I remember this is I remember it by simply saying the derivative of the product is the first times the derivative of the second plus the second times the derivative of the first. Also notice that in this formula, because we're adding the two products together, it wouldn't make a difference. I'm going to say the order in which we take the product, as long as I'm going to say it's the correct mixture of keeping one function and taking the derivative of the other. However, I will say that when I do this in the notes, I'll always do it in this order. You guys need to find an order that works for you and use it every time. So let's look at using the product rule to find the derivative of this first function. So you notice, first of all, that this is a product of two binomials. Now, we're going to run into situations where we don't have just one way to find a derivative. I want to exemplify the product rule, so I'm specifically going to use the product rule here. But notice that you could actually FOIL these two binomials out and then just take derivatives as we've learned in the prior lesson. In this particular example, I'm going to rename this first function as u and then the second function as v. And then that way I'm able to better use my formula from up above. I'm going to say a simplified version of the formula is something that looks like this. So I could say y prime is equal to first times derivative of the second plus second times derivative of the first. It's just kind of a simpler version if you want to use that one instead. And so that's what I'll do here. So that would simplify down. U, if I keep it, is just 4x to the third minus 2. And then now I want to multiply that by the derivative of the second. The second, I would use the the power rule on this first part. I have the 3x squared, so I'd multiply the 2 by the 3 and then reduce the power of 2 to 1. So that would end up being 6x. And then the derivative of the 4 would just be 0. So far I have the first multiplied by the derivative of the second. Then from the formula, I have the plus symbol. And then the next piece in the formula says keep now the second piece of the product. So 3x squared plus 4. And then multiply that now by the derivative of the first piece. For the derivative of the first piece, we'd multiply the 3 by the 4, that'd be 12. And then we'd reduce the power of 3 to 2. So that would be 12x to the second. And then the derivative of negative 2 would be 0. So that we wouldn't write. All right, and then from here, what I'm going to do is two things. I'm going to go ahead and distribute, in other words, multiply these out, and then before I'm finished, I'm going to check and see if I can factor. When we can, we want to leave derivatives in as nice a form as possible because of some of the things we're going to do later on, so we want to try to factor these if we possibly can. So let me first distribute. So I'm going to distribute the 6x into here. So that would be 24x to the fourth, and then minus 12x. All right, and then over here, be careful of the sign. This sign would obviously always be positive, but in other problems where we deal with quotients, that symbol will actually be a negative, and there'll be, I'm going to say, a more involved type of problem. But be careful there. Notice that's positive, so that's not going to influence anything, so we are safe just to distribute this 12x squared through. So we'd have 12 times 3, 36. And then the x squared times the other x squared would be x to the fourth. And then 12 times 4, 48. And then that would be an x squared. All right, it looks like there's a couple of terms we can combine. I'm also going to put my terms in descending order. So we notice the highest power I have is to the fourth. I'm going to say it looks like we have a 24 and a 36 that we're able to add together. So that would end up being 60 x to the fourth. And then looks like the next highest power would be my 48 x squared. And then the last highest power is the negative 12x. All right, and then from here to complete the problem, we notice that 60 and 48 and negative 12 all share a factor of 12. And we also notice that we have x's in common to all terms. So we want to factor. So factoring out a common factor of 12x, that would then leave me with 5x to the third, and then plus 4x. And then here, just minus 1, since that factor is the actual greatest common factor, I need to leave a negative 1 there in its place. So that would be the derivative of my original problem using the product rule. All right, let's now look at the second example down. We notice on this particular problem, it's actually not written as a product right now. This is what we call composition functions. In other words, it's a function that's all squared. The inside part happens to also be another function, 2x minus 1. So later on, we're going to learn a different method for doing this particular problem that's actually easier. But for right now, since we're working on product rules, I want to rewrite this. We know because it says it's squared, that means that you can write the binomial multiplied by itself. Okay, so we're going to write it that way, and obviously that's a product. So using product rule, we'll say y prime. When you're first starting to do this, it's a good idea to label so that you can see what you're doing. So there's u, and here's v. It's also a good idea the first couple of times that you use a formula, I'm going to say until you get the formula down, rewrite it. So the formula is the first times the derivative of the second plus the second times the derivative of the first. All right, so our first function is 2x minus 1. The derivative of my second function would be the derivative of 2x minus 1, which would just be 2. And then from the formula plus, and then my second function is 2x minus 1. And then multiplied, derivative of the first, well, it's 2x minus 1 is the function, so the derivative is 2 again. And so we get that. All right, I'm going to go ahead and distribute. So this becomes 4x minus 2, as does this piece. And then combining, I have a 4x plus a 4x, so that's 8x, and the negative 2 minus a 2, so that's minus 4. And then once again, we're going to factor that. We notice we have a common factor of 4, so we can pull a 4 out. We'll be left with a 2x minus 1. So there's the derivative of my original function by using the product rule. All right. So now we're going to look at a much more involved type of problem. This one you have ugly exponents. I'm going to say is kind of a nastier type question. So once again, I'm going to come up and I'm going to label. We notice it's definitely a product. So I'm going to label the first as u and the second as v. Here, instead of saying y prime, I'm going to say p prime of x. I'm going to go ahead and copy down I'm going to say definition until I've got it down. So it's the first times the derivative of the second plus the second times the derivative of the first. You may want to continue doing this. It just kind of gives you a nice formula to plug and chug into. All right, the first is just the x to the negative 1 plus x to the negative 2. And then derivative of the second, we'd multiply the negative 3 by the 2, so that'd give us negative 6x. And then this is negative 3. If we subtracted 1 from that, we'd get negative 4. Okay, coming over here, we'd have a negative 4 multiplied by the negative 5, so that's 20. And then we're going to reduce that original power by 1, so that would become to the negative 5. All right, and then from the formula plus, we now keep the second part of the product. So the 2x to the negative 3 minus 5x to the negative 4th. And then multiply by the derivative of the first. So on the first, you have that negative 1. That would be multiplied to the front, so it becomes negative 1x. and then reduce the power of -1 to -2. And then on the second one, that would be -2x to the -3 when you take its derivative. All right, now, this particular problem, I'm going to say just by nature of the problem, ends up having an uglier type of reducing. We see that you basically have a set of two binomials that need to be multiplied together, and then we're eventually going to sum them, so we're going to have to combine like terms and such. So the first thing we need to do is FOIL all this good stuff out. All right, so I'm going to be very careful there. We remember that when we multiply the coefficients in the front, and then we add the exponents. So here, there would be obviously an understood 1 in front of this one and in front of that one. Okay, so when you multiply the first two here, this one by that one, we'd be multiplying the 1 times the -6, which would give us -6, and then you'd be multiplying the x to the -1 times the x to the -4, which means you're going to add those two exponents. So that would become x to the -5. All right, now when we do the outer, these guys out here, we're multiplying 1 times 20, which is 20, and then we're adding the exponents -1 and -5. So it would become x to the -6. All right, now we're going to do inner, so these two terms. We'd multiply a +1 times -6, so that's -6. And then add the exponents on the x's, so -2 plus -4 would be x to the -6. All right, so we've done first, we've done outer, we've done inner, and then all we have to do now is the last two terms. So this term and that one, we'd multiply the 1 and the 20, so we'd get 20. And then when we add those exponents, we'd get x to the -7. So we've got that piece taken care of. All right, then we have the plus sign from up above. I'm going to use a different color there so you can see the two pieces separated. And then we come over and we need to FOIL out that next group of stuff. Okay, I'm going to do that a similar way. I'm not going to draw the arrows on this one, so when I do the first two, I'm going to get actually -2x to the -5. When I do the outer two, I'm going to get -4x to the -6. When I do the inner two, I'm going to get +5x to the -6. And then when I do the last, I'm going to get +10 and then x to the -7. Okay, so we want to be really careful in here watching our signs. Obviously, it'd be really easy to make a mistake somewhere. All right, now what we're going to do is come back and combine like terms. I'm going to go ahead and do descending order. So looking at descending order, let's see what the, quote, highest power is. We see here all of our powers are negative, but I'm just going to take it like I would a regular problem. So there's two of my highest powers there, so that's a 30x to the -7. All right, what's the next highest powers? It looks like -6s. So powers of -6s here, 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 and here. Get that one underlined. All right, so on there, I'm going to say kind of depending on the order that you want to combine those in, you can just stick in the coefficients on your calculator if you'd like to. That would be totally fine. So it would be a 20 minus a 6 minus a 4 and then plus a 5, and you're going to end up with 15. And that'll be x to the -6. And then it looks like that leaves my x to the -5s. So there it looks like we're going to have -8x to the -5s. All right, and then from here we know that we can't leave negative exponents in our answer. So what we're going to do there is the coefficients in the front, those are our numerator values. So this 30 would be in the numerator, and then the x to the -7 would fall to the bottom and become x to the +7. This one we'd have the 15 in the numerator, and then x to the 6th in the denominator. And this one we'd have the -8 in the top, and then the x to the 5th there in the bottom. Now, at a later stage, it's going to become necessary for us to find common denominators and actually combine these together. For right now, we can leave it like it is and be okay as far as entering our final answers. So I'm going to block that in and say for right now, that's an okay way to express our answers. All right. So once again, in this section, it's my goal to throw at you as many examples as I can so that you can see the problems that may pop up in your notes or on quizzes, tests, and so forth. All right, this particular problem is definitely a product. However, the second piece of that product needs to be rewritten, similar to the way we rewrote certain problems in the last section. So the 2x minus 3, that part's good, but the second part needs to be written as x to a power of 1/2 and then minus 1. Anytime you have a root, you want to rewrite that root as a fractional power. Okay, now we can identify here is our u and here is our v. And so now let's go find the derivative. So y prime equals, it'll be the first times the derivative of the second, and then plus the second times the derivative of the first. So on this one, the first is 2x minus 3. The derivative of the second, we would say take that 1/2 and multiply it to the front. I'm going to go ahead and write this step for right now. We're not totally comfortable maybe doing these yet. It would need to be 1/2 minus 1. Remember, we do a clever one by writing it with the same denominator as whatever fraction that is. All right, and then that takes care of the derivative of the first part, and we'll reduce that power here in a minute. The derivative, notice, of -1 is 0, so we're good there. And then we're going to say plus from the formula, and then we want to keep the second, so x to the 1/2 minus 1. And then we want derivative of the first. Derivative of 2x is just 2, derivative of -3 is 0, so derivative of that first piece is 2. All right, let's simplify a little bit here. So this is 2x minus 3. This is 1/2, and then notice that this would be x to the -1/2. All right, over here, if you want to go ahead and distribute, we can definitely do that. So that would be 2x to the 1/2 minus 2. And then I'll go ahead as well here and distribute. Notice that that's a single term, so it can be distributed to both of those. When we take 1/2 and multiply by 2, the 2's would cancel, and we're going to be left with 1. Now notice here that this x has an understood power of 1. However, we're wanting to add the -1/2 power to it. So if you want to, think of that power as a 2 over 2, because that would be convenient. And then remember here, we're adding the powers. So 2 over 2 minus 1 over 2 would be 1/2. So the power here would be x to the 1/2. Okay, and then multiplying into the -3, you can think about the -3 over 1. There's nothing that would cancel there, so you're going to end up with negative. You multiply the 3 by the 1, multiply the 1 by the 2, so -3/2, and then that x to the -1/2 just tags along on that part. All right, and then we're going to keep these guys over here. All right, from here, we're going to see if we have any like terms. It looks like we have at least a couple. We see a like term here. We can add those together. That would be 3x to the 1/2. One thing you do have to be careful about is in these problems, you're both multiplying as well as combining like terms. Remember that when you multiply and you have x to powers, you add your powers together. But when you're adding like terms, like we just did, you keep your power. So you're basically just counting how many of them you have. You're saying I have 1x to the 1/2 plus 2x to the 1/2 would be still 3, but it's still a 1/2 power. All right, we don't have any more like terms, so we'll just write it. On this one, we'll go ahead and drop that negative to the bottom. So it's 3 over 2x to the positive 1/2, and then minus 2. Okay, and on that one, you could leave your answer like that. That would be okay. Or if you'd rather write it in root form, we can do that as well. This would be 3 square roots of x, and then minus 3 over 2 square roots of x minus 2. All right, the next thing we're going to look at is the quotient rule. This is saying that if you have a function that either is written as a quotient or can be written as a quotient, and here we're going to have u of x in the numerator and then v of x in the denominator, then the derivative is found by using this formula. This formula looks kind of big and ugly, so here's what I'll do for you. Basically, the formula says we're going to take the denominator of the original problem and then multiply it by the derivative of the numerator, and then minus, we're going to take the numerator and then multiply it by the derivative of the denominator, and then take all that and divide it by the denominator all squared. One way that we remember this in, I'm going to say kind of shorthand, is by saying the derivative of a quotient is low d high minus high d low over the square of what's below. And where we're saying the d, that means we're going to take the derivative of that particular one. So on here, for this particular problem, let's go ahead and start it by labeling. So let's say that we call the top U and the bottom V. I'm going to go ahead and write down our formula for the quotient. So when I take the derivative of this particular function, we're going to say that we start with low, so that would be V times derivative of high, and then minus high times derivative of low, and then over the square of what's below. So we always make sure use parentheses or brackets or something like that when we square the denominator. All right, so let's go ahead and do these operations. So V means that we just keep the denominator. So that's 3x minus 4. And then U prime means we take the derivative of the top. Well, the top is a constant in this situation, so that's going to be 0. And then in the formula, there's a minus. Now, we've discussed when you do the product rule, it doesn't really make a difference the order in which you do the product rule as long as you have the right combination. In this particular formula, you must do the formula in this particular order because of the minus sign that we see in the top, and we have to be especially careful of that negative sign as well. All right, U was 2, so we just keep in the top, and then we want the derivative of the bottom. The bottom is 3x minus 4. When we take the derivative of 3x is just 3, derivative of negative 4 is 0, so that derivative is just 3, and then all of this is over the bottom squared. Okay, you can use bracket, parenthesis, whatever is, I'm going to say, most applicable for the problem. On this one, I'm going to use parenthesis, 3x minus 4 all squared. All right, from here, we're going to reduce. Now notice that this whole first piece is multiplied by 0, which means that whole part goes to 0. Okay, so that means that in the top, really the only thing left is the negative 2 times the 3, so that'll be negative 6, and then this is all over 3x minus 4 all squared. Now, on these type of problems, what we want to do is at the end of them, make sure that everything is factored completely. If it's not factored completely, we want to go ahead and try to factor so that if we see any factors that can reduce, we can go ahead and do that step. We see here in the bottom, 3x minus 4 is factored indeed. The negative 6 on the top, it's in factored form. There's not anything that's going to cancel. Do make sure y'all remember that you cannot cancel terms. So in other words, maybe the 3 and the 6 share a factor of 3. Well, 3x, because it's subtracted by the 4, is a term, so you can't cancel terms. So just be careful there. All right, this next problem down, we'll do the same thing here. So we're going to say the top will be U, the bottom would be V. So taking the derivative, we'll say f prime of x equals, all right, we say we start with the bottom, so it's V times derivative of the top, and then minus the top times derivative of bottom, and then all over the bottom piece squared. All right, from here, we're going to go ahead and plug in. So the bottom is the 3x squared plus the 1, and then derivative of the top. This one, derivative of negative x squared would be negative 2x. Derivative of 2x would just be 2. All right, and then from the formula minus, u use the top, so that would be negative x squared plus 2x. And then over derivative of the bottom. Derivative of the bottom would be 6x. Derivative, obviously, of the 1 would have been a 0, so that doesn't make a difference. And then all of this is over the bottom squared. Okay, now I'll tell you, on these particular problems, we're going to do quite a few of these because the algebra can get ugly. And I want y'all to be comfortable with the algebra from these problems. You're also going to need to be very patient. All right, from here, what we're going to do next is we're going to go ahead and FOIL. So we see here we have two binomials. And so we're going to FOIL those two binomials out. Now, in a later section, at this particular point, we're going to end up, I'm going to say, doing some more complicated problems. And we're going to get past the point where we're wanting to FOIL. So there'll be uglier, nastier kind of things. And I'm going to show you all a trick. And that trick that I show you, if you later on realize it applies to some of these questions, can be used on these questions. So this is not the only way. The way I'm showing you here is not the only way that you can simplify these. All right, so I'm going to use purple here to FOIL out these two terms. So if I multiply first and first, that would end up with negative 6x to the third. When I multiply the outers, that would end up with 6x to the second. The inners here would be negative 2x. And then the last is plus 2. All right, now from the formula, we have the negative sign. So there's the minus from the formula. One of the big things with the quotient formula is now, I'm going to say, is a time where there potentially could be an error made because of that sign. So now notice that this 6x needs to be distributed to these two things. So what I'm going to tell you to do there is put a parenthesis here after this negative, and even though you're distributing at this point, you still later need to distribute this negative. So on this particular part, I'll do it in the maroon, we're going to have 6x times negative x squared, so negative 6x to the third, and then 6x times the 2x, so that would be 12x squared. All right, and then all of this is still over the denominator all squared, the original denominator all squared. So it's still over 3x squared plus 1 all squared. All right, I'm going to go ahead and distribute this negative. And then we're going to see if we can wrap it up by combining like terms, and then maybe see if we can factor before we finish. So negative x to the third plus 6x to the second minus 2x plus 2, and then plus 6x to the third minus 12x squared. And then all over still the bottom squared. Now, the bottom, you don't ever actually have to square that. So in other words, I'm not ever going to ask you to write it twice and FOIL it out. The general idea is sometimes the denominator will actually cancel with another factor. So we want to leave it in factor form if we possibly can. All right, so now we're going to combine like terms, and I'm going to do so by trying to do descending order. On this one, you see we have a negative 6x to the third and a positive 6x to the third. So those two actually cancel. Then we have a 6x squared minus a 12x squared, so that's actually negative 6x squared. And then let's see here, it looks like we then just have a negative 2x and a plus 2. And then that's still over the denominator squared. All right, from this point, we want to try to factor as much as we possibly can so that if anything cancels, we can cancel it out. We notice that the top has a factor of definitely 2 in common. If the very first term here is negative, we'll factor out a negative along with that. Looks like that's the only thing that's common as far as the greatest common factor. So we're going to factor out a negative 2. That leaves us here with a 3x squared. And then plus x in this case because we factored the negative out, and then minus 1. And all of that is over still my 3x squared plus 1 all squared. Okay, now this inside piece looks like it's possibly factorable, and you'd want to check to see if it were factorable. Okay, now I'm going to say I have already checked so I can save us that time, but just be careful. This is a trinomial. It definitely looks like it can factor. If it can, you go ahead and go on that extra step. This particular one ends up being prime, so we're going to leave it at that location there. Okay, so there's our, I'm going to say, overall result for the derivative of that quotient. All right, so we've seen that these problems are definitely getting a good deal uglier as far as the just look of the problems. The other thing is there's quite a few steps, and so it's really easy to miss something somewhere and to overlook a sign or a number, something along those lines. From this step to this step, as far as that back piece that I was talking about here, being careful with this green negative from that step to that step. What I'm showing you here is the thing that I've had the best luck with as far as making sure students don't make errors. Go ahead and bring that negative sign down, making sure you have that set of parentheses, and then waiting until the next step to actually distribute it through. I've taught this for a good many years, and I used to teach this in a different way, and I've had better success with this particular method. So I always try to show you the method that I feel like is going to cause you to make the least amount of errors. All right, let's now go to this problem here. This one, we notice it involves a root of x. We always want to rewrite those having fraction powers. So let's rewrite this original question as 4x to the 1/2, and then plus 3x. And then all of that is over 2x plus 7. All right, we're going to call the top part up here u, and the bottom part down here v. All right, so let's take a derivative. So y prime equals, we're going to go ahead and write our derivative formula out. Most important that we start with the bottom function, so v times the derivative of u, and then minus u times derivative of v all over v squared. All right, so on this one, let's go ahead and plug and chug. So the bottom is 2x plus 7, and then the derivative of the top, we'd have to take 1/2 and multiply it by the 4. Well, so I'm going to go ahead and write that step out. So it'd be 4, and then you're multiplying by the 1/2. And then you're also reducing that original power of 1/2 by understood 1. And we're going to subtract it as a 2 over 2. So there's that first piece. And then plus derivative of the second. I'm sorry, not the derivative of the second, but the derivative of the second piece in the top. That would be 3. Okay, so that's taking care of bottom times derivative of the top. And then we're going to do minus. And then we want to do top. So that's 4x to the 1/2 plus 3x. And then we want derivative of the bottom. Derivative of the bottom would just be 2. And then all of that is over the bottom squared. Right? From here, we're wanting to simplify. Okay, I'm first going to simplify my powers and my numbers on that first group of stuff. It's still kind of ugly. So let's do that first. We have 2x plus 7. And then multiplied, we have 1/2 of 4, which would just be 2. This would be x to the negative 1/2 power, and then plus 3. And then over here, I'm going to keep the negative. I can distribute that on the next step, but I'm going to go ahead and distribute this 2 through. So the 2 multiplies to the front, so be careful here, it goes to the 4. So it goes 8x to the 1/2, and then 6x. And remember in the denominator, just to leave the denominator as that whole group squared. We don't actually want to FOIL it out. So 2x plus 7 all squared. All right, and then from here, we unfortunately have to FOIL out those 2 binomials. So let's go ahead and do that. Now I'm going to say a placeholder, and I'm going to use the placeholder that's convenient for me at this moment. When I multiply these first 2 together, I'm going to have to multiply the numbers in front, so 2 times 2 would end up being 4. And then, though, I'm having to multiply the x, I'm having to multiply the x by the x to the negative 1/2. There, remember, we add our exponents. Well, if we're trying to add exponents, it would be most convenient if this exponent was written as a 2 over 2. Okay, so that exponent was an understood 1, but if we write it as a 2 over 2, then I can see I can add those easier. So this would become 4x, and then if we add 2 over 2 plus negative 1/2, we get 1/2. Okay, so we've multiplied the first and the first. Now we need to multiply the outers. So 2 times 3 would be 6. At this point, it's more convenient just to think of this as just an x. So 6x. Multiply the inners. So it'd be 14, and then x to the negative 1/2. Multiply the last. So that would be 21. Okay, so we FOILed out those first 2 binomials. Okay, now distribute this negative. So this would be negative 8x to the 1/2, and then minus 6x. and then all over the bottom thing squared. All right, from here we want to try to combine like terms. All right, so let's see. We have a 4x to the 1/2 and a negative 8x to the 1/2. So that would be negative 4x to the 1/2. All right, I'm going to go ahead and put the other 1/2 power next. I have a plus 14x to the negative 1/2. All right, I have a 6x and it looks like a negative 6x that are actually going to cancel, so those are gone. And then we have a 21. Okay, and then all of that is over 2x plus 7 all squared. All right, now this particular part becomes very, very important, and I'm going to say you'll see it in other problems, and you need to know what to do and what not to do. And what I'm going to be talking about is I'm going to be talking about what to do with the term specifically that has the negative exponent on it. You know that you can't have negative exponents in your answer. Okay, but here's the deal. That particular term that has the negative exponent on it is just that. It's a term. It's something that was added to other pieces of the problem. So in this situation, because it's in the numerator of a, I'm going to say kind of nastier looking problem, and it's a term in the numerator, okay, so there's other stuff around it, you can't just take it to the bottom and change that exponent to a positive x to the half in the denominator. Now, what you're going to do, though, is you're going to create a fraction with just that one term. You're going to put it over 1, and you're going to take that x to the negative 1/2 and drop it to the bottom of only that one single term. So it's going to look like this. So it'll be negative 4x to the 1/2 plus, the 14 is in the numerator, so 14 over x to the 1/2. And then plus 21, and then all that still over the bottom stuff squared. All right, so you're still going to make it a positive exponent, but you have to be careful how you do that since it's wrapped up in a group of other things. All right, now from here, on this particular problem, I am going to rewrite the half powers as roots. And I'm going to say one of the reasons I'm going to do that, it just makes it easier to see what I'm about to do. What this is now called is called a complex fraction because the whole thing is a fraction. And then there's one piece now because I made that exponent into a positive that's also a fraction. So a fraction within a fraction is a complex fraction. So on here, I'm going to go ahead and rewrite the x to the 1/2 as roots of x's. And the only reason I'm doing that is sometimes our brains just do better with the roots as opposed to the half powers. All right, and then for complex fractions, to reduce them to their proper forms, you have to clear out any kind of complex fractions. So what you're going to do is you're going to look in the denominators. So like this one is over 1. This one's obviously over square root of x. This one's over 1. This one is over 1. So look at, I'm going to say denominators that are not 1s. The 1s aren't going to make any difference. So on this one, the denominator that's not a 1 is the square root of x. That tells you that your least common denominator would be square root of x. So what you're going to do is you're going to multiply every single term that you have in this problem by a square root of x. So you're going to take the top group, multiply by square root of x, and you're going to take the bottom group and multiply by the square root of x. All right, and what this will do is it will clear out your fractions. All right, we're going to distribute. So distributing there, we get negative 4. And then what happens if you do root of x times root of x? Well, you get root of x all squared. Okay. On the next piece, you have 14 over root of x times root of x. What happens when you do that? Well, eventually, because this is over root of x and you're multiplying by a root of x, those roots of x are going to end up canceling out. Okay, and then at the end, the 21's over 1. The over 1 part in this situation really doesn't make a difference. So you're going to just end up with 21 times root of x. Now, in the denominator, we notice that the bottom part's squared. All right, now in the denominator, we notice that the 2x plus 7 all squared is over 1. The over 1 was just for me to point out, hey, we can make that look like a fraction, it would be over 1. So we don't really want that or need that at this point. So we're going to leave the bottom factored. So we want it 2x plus 7 all squared still. And then we're just going to tack on the root of x next to it. And it's going to stay that way unless something cancels out. All right, from here, let's simplify. When you do negative 4 times square root of x squared, the root and the square cancel out. So we get just negative 4x. All right, we've already seen here that that root of x is going to cancel out, so that's going to leave us 14. And over here, we're going to get just 21 roots of x. And all of this is over the 2x plus 7 all squared times root of x. Okay, now, at this point, what we'd want to try to do is we want to try to factor if we possibly can. The bottom is already in factored form. The top, we notice that there's not any numbers in common, so it's not like we could factor out a common factor. All the terms don't have x's on them. Even if they did, one of the x's is stuck up under a root. So this particular problem is done. It's not factorable. There's nothing we can do to simplify it out. It's just kind of an ugly looking question. Okay, so we're good on that answer there for the final result. All right, so now let's look at this particular problem. This is going to be one where later on we're going to learn another rule, and in learning the other rule, we're going to learn other ways to simplify. May or may not help us out as far as these questions are concerned. All right, let's take a look at this particular problem. All right, let's take a look at a more complicated type problem. This particular one, notice that it's actually kind of a combination of both a product and a quotient. So we notice that here in the top, there's actually a product of two things, and then the whole thing is a quotient. I don't want to try to use a product and a quotient rule in the same problem if I possibly can keep from it. So what I'm actually going to do is I'm going to take this and I'm going to rewrite it, and I'm going to FOIL all this good stuff out. All right, so on this particular one, I'm going to multiply the 3x squared by the 4x. So that will give me 12x to the third. And then I'm going to multiply the 3x squared by the 2. So that'll give me 6x squared. And then the 6 by the 4x, so 24x. And then finally the 6 by the 2, so 12. And then all that is over the 6x minus 7. All right. I will say there's one thing that I can do on this problem that will save me a little bit of work at the end. And you can either choose to do this at the beginning of the problem, or you can do it at the, just kind of go ahead and realize you'll have a little bit more work to do at the end. I'm going to go ahead and do it as an introduction to something we're going to see later on. Notice that the top has 6's in common. So if I were to factor a 6 out, then on this one, we're going to end up with a 2x cubed, and then plus just an x squared, and then there plus a 4x, and then plus a 2, and then all over the 6x minus 7. Now, I'm going to somewhat cheat when I do this problem, and here's what I mean. We know that we have a rule that says it's a constant multiple rule for derivatives. So essentially, if you have a constant of some kind, you can take the derivative of the more interior part, and then just when you're done, multiply the result by the constant that you had in the front. So we're going to somewhat separate that 6 out, and we're only going to work with that inside part as far as doing a derivative. We're going to call the top part u and the bottom part v. That 6 is going to stick with me throughout the problem, but it's kind of like I've already factored this problem partially, and that will help me have not quite as big a numbers throughout this problem. All right, so doing my derivative, I know I start with the bottom, and then I multiply by derivative of the top, and then minus the top times derivative of the bottom, and then all over the bottom squared. Now, the exception here is because I have this constant of 6 sitting out in the front, then when I come down to actually work the problem, I'm going to make sure to write that 6, and then now I'm going to start working with this rule here. All right, so the bottom was 6x minus 7. And put that in parentheses since that was a whole group. And then I want the derivative of the top. Okay, the top, obviously a longer kind of thing, but I'm just going to take derivative of each piece. So derivative of 2x cubed would be 6x squared. Derivative of the x squared would be 2x. And then derivative of 4x would be 4. So there's that part. And then minus, we would say top, which is this big long thing, and then derivative of the bottom. And then derivative of the bottom. So that would be times 6. And then all that is over the bottom squared. And I'm going to finish bracketing out so that we can see all that still multiplied by the 6 in the front. All right, so remember what I said a while ago about patience. This is going to be one of those problems that's going to just take a little while as far as to complete it out. All right, from here, what you're going to have to do is multiply these two groups of things together. The bad news is they're not binomials, so you can't FOIL them out. So literally what you're going to have to do is first take the 6x and you're going to have to multiply it by all three of these terms. And then when you're done, you're then going to take the negative 7 and multiply it by all three terms. Okay, so I'll color code those so we can see kind of what we're doing. All right, so 6x times 6x squared would be 36x to the third. 6x times 2x would be 12x squared. And then from there, the 6x times the 4 would be 24x. All right, and then now I'm going to switch to this negative 7. Negative 7 times 6x squared would be negative 42x squared. Negative 7 times 2x would be negative 14x. And then negative 7 times the positive 4 would be negative 28. All right, and the next part, remember we have a minus right there, so I'm going to keep that negative sign and I'm going to put a parenthesis around whatever I'm doing next. Notice that this 6 is going to end up getting distributed. So distributing the 6, we'll end up with 12x to the third, and then plus 6x squared, plus 24x, and then plus 12. Okay, and then all of that is still over the bottom thing squared. And remember there, we're just going to keep it squared for right now. All right, and then still brackets. It's never good when your instructor gives you a whole page to work a problem. You know that means it's going to take a little while. All right, so keeping this 6 in the front. Okay, I'm going to combine any like terms that I can with the green and the purple part, and then eventually here I'll distribute negatives, and then combine any remaining like terms on the next step down. All right, so far I have this 36x cubed. I don't see any more cubes here in the first part. I will eventually be able to combine it with something else. Let's see here, squares. So it looks like here I have the 12x squared and the negative 42x squared. So those two guys can definitely be combined. So that would give me a negative, and then that's going to end up being 30x squared. And then looks like we can combine also the negative 14x with the 24x. So that'll give me a 10x and then negative 28. Okay, distributing this negative, I'll have negative 12x cubed minus 6x squared minus 24x and then minus 12. And then all that over the bottom piece, all squared. All right, and then let's combine like terms and then see if there's anything additionally that we can do. All right, so from here we have a 36x to the third minus a 12x to the third. So that's going to be 24x to the third. All right, from there we have x squareds. So we have a negative 30x squared minus a 6x squared. So that's negative 36x squared. All right, from there, it looks like we have a 10x and a negative 24x. So that's going to give us a negative 14x. And then at the back end over here, we have a negative 28x and a negative 12. So that's going to end up giving us negative 40 at the back. And then all this is still over the 6x minus 7 all squared. All right, from here, we want to try to factor as much as we can. Notice we did have already that 6 that was factored out in the front. All right, with the remaining numbers, we have a 24, we have a 36, we have a 14, and we have that negative 40. So we notice for sure that they all share a factor of 2. I don't believe we can go any larger with that factor. So what we're going to do is take a factor of 2 out of each of those, and then we're going to multiply it by the 6 that was already out in the front. Okay, so there we'll say 6 multiplied by this factor of 2 that we're pulling out. Okay, and then we're dividing each of those by 2, so this would become a 12x to the third, and then minus, and then there dividing that by 2, negative 18x squared, minus 7x, and then here, minus 20, and all that over 6x minus 7 all squared. All right, now the top of this is something that we have not talked about yet in this course, and that is when you have 4 terms, sometimes we can do what's called factor by grouping. This particular problem, the numbers aren't correct to do factor by grouping, so we've actually factored at this point all that we can. Final thing we need to do is rewrite this 6 times 2 out in the front just as a 12, and then just copy down what we had on the inside, and then that would be our final answer for this particular problem. Okay, on your exam, then if you run into problems like this, they're going to tell you, I'm going to say to do the simplification that you're used to doing, in other words, factor, cancel. So there's going to be specific instructions that are going to indicate to you when you get to the end of problems like these, there's, I'm going to say, additional steps that need to be done that would include this factorization that we've done here at the end. All right. So now let's move on and look at finding equation of a tangent line when you have a function that's a quotient that you're needing to find the equation of the tangent line at. So on this particular one, what I'm going to do is I'm going to cheat a little bit because I know that if I have to take a derivative and it's a quotient type problem, then my derivative ends up being a little bit more difficult. Here, I know specifically I want the derivative only at, I'm going to say, the point of interest. So on this particular one, notice that my x value is 2. So I want the derivative specifically at x is equal to 2. So what I'm going to do is I'm going to first very generally find my derivative, and then immediately I'm going to plug in 2 anywhere there was an x, and then that way I don't have to simplify out ugly algebra. I'm simply simplifying out just arithmetic. So on here, let's first find the derivative. Okay. So we start with the denominator, which is 2x minus 3. And then we take the derivative of the top, which is 2. And then minus, we keep the top. And then take the derivative of the bottom, which is 2. And then we put that all over the bottom squared. All right. What we've done before on these kind of problems is we distribute the 2's, distribute the negative, combine like terms, and so forth. And you can still do that if you'd like to. Or, because this particular problem only wants the derivative at x equals 2, what we could now do is do specifically, hey, the derivative at 2 and then plug 2 in everywhere there's an x in this problem. So 2 times 2 minus 3 times 2, and then minus 2 times 2 minus 5 times 2, and then all over 2 times 2 minus 3 all squared. And I think that's just a simpler way to maybe work the problem. All right, from here, I'm going to go ahead and do my arithmetic. So 2 times 2, that's going to be 4. 4 minus 3, that's going to be 1. And then 1 times 2, that gives me 2 there on the first piece. And then minus from the problem. 2 times 2, that's 4. 4 minus 5, that's negative 1. Negative 1 times 2 would be negative 2. And then all over in the bottom, 2 times 2 is 4. 4 minus 3 is 1. 1 squared is 1. So essentially here I get 2 minus negative 2, which ends up being 2 plus 2, which is just 4. And that's over 1. 4 over 1 would just be 4. So that would be my slope. Okay. From here, we already have a point given. So we know that our 2, sometimes we label that as x1. Our y would be, our y1 would be the negative 1. So really we can kind of skip a step that we normally have to do and go straight to here. All right, so we're going to do y minus negative 1, and then that equals, our slope we found was 4, and then x minus 2. So at this point, y plus 1, distribute this 4 in, so 4x minus 8. Okay, and then I think the only thing we've got to do is subtract the 1 over. We want always this to be in y equals mx plus b form, so y equals 4x minus 9, and then that's our equation of our tangent line. So we kind of had a nice trick in here that made that particular problem just a little bit easier since we were trying to evaluate specifically at the x value of 2. All right, let's look at some more economics type applications. So if we're given that C of x represents the total cost to manufacture x items, then there's this thing that we call average cost. The average cost, we use a particular type notation. Y'all see here, basically it's my C of x function with that horizontal bar over the top of it. So do be careful there. Okay, and that definition is that the average cost is found by taking the cost function and dividing by x. So you need to make sure here that you understand the notation for average cost. It's the cost function with the horizontal bar over the top, and the actual formula for that is found by taking the cost and dividing by x. Now, for us specifically, sometimes they'll ask for the marginal average cost. That means you've got to do two things. You have to find the average cost function, and then y'all remember marginal means you take the derivative. So marginal average cost is represented using this formula. All right, so let's say that the cost in dollars of manufacturing X 100 widgets is given by C of X equal this function, and we notice that it's a quotient. So it wants us to find the marginal cost. So it's always a two-step type of question if it asks for marginal average cost. Notice down here that the C part is asking for marginal average cost. The A part is just asking for the marginal cost. So we're saying, hey, you need to go to the cost function and you need to find its derivative. Okay. So we're going to say derivative of the cost function and use the quotient rule. So we say keep the bottom, take the derivative of the top, and then minus, keep the top, and then take the derivative at the bottom. On this one, we haven't run into anything like this so far, I don't think. If we have on this one just an x plus a 2, we know derivative of 2 would be 0. The x, there's the understood 1 in the front. So derivative of x is the constant in the front, which would just be 1. And then all of that is over the bottom squared. All right, we're going to go ahead and simplify this down. Notice over here on the second part, we're multiplying by 1, so the 1's not going to affect anything, so it's safe on this part to eventually just distribute that negative. On the first part, it looks like we're distributing a 2. So we have 2x plus 4, and then minus 2x minus 25, and then all over x plus 2 all squared. All right, let's simplify that down as much as we can. We notice there's a 2x and a negative 2x that would cancel. We have a 4 and a negative 25, so that'll give us negative 21, and then all over x plus 2 all squared. Okay, so if they ask you to find the marginal cost, then that means you take the derivative of just the cost function itself. All right, now the next piece says find the average cost. The average cost is the cost function divided by x. Well, I'm going to say if the cost function is already a quotient, then dividing by x is going to make it really ugly. So what you can do is, if your cost function is already a fraction, you can basically just multiply by an extra factor of x in the denominator. So the average cost function, the notation is this. And then I'm going to take the fraction 2x plus 25 over, and then in the denominator, I'm going to put an extra x multiplied by the x plus 2 that's already there. So that's a legal way to find your average cost if your cost function's a fraction. Now, what I want to do, though, is I want to go ahead and, in this case, simplify this out because I know that I'm about to need to take its derivative when we say marginal. This is also another problem where you end up with a product in the denominator and the overall problem is a quotient. So I really don't want to have to use a product and a quotient rule in the same problem. So in this situation, it's better for me to go ahead and multiply that denominator out so that my actual work is not so bad on the next piece. Okay, so there is my average cost function. All right, find the marginal average cost. This would involve first finding your average cost, which we've already done, and then because it says marginal, then that means I'm going to take the derivative. So the proper notation here would be C of x with a bar over the top, put that in parentheses and say prime to say now we're taking the derivative. Okay, I'm going to say the average cost function was a quotient, so we're going to have to use quotient rule here. So we're going to say it's the bottom times the derivative of the top minus the top times the derivative of the bottom and then all over the bottom squared. All right, and then we need to simplify this out. All right, so from here, I'm going to go ahead and distribute this 2. So we've got 2x squared plus 4x. I'm going to keep the minus, and then I'm going to put a big parenthesis here, meaning that eventually that negative is going to be distributed. Notice on the second group of stuff, I'm going to have to FOIL it. So I'm going to change colors here so you can see me do that. So now foiling that, I'll get 4x squared plus 4x plus 50x plus 50. And all over the bottom squared. All right, and then from there, I'm going to go ahead and distribute this negative into here. And then on the next step, we'll simplify and see if we can do any kind of factorization. So 2x squared plus 4x. And then go ahead and distribute that negative. So minus 4x squared minus 4x minus 50x minus 50. And then we're keeping the bottom. right, from here, let's see if we can cancel or simplify anything. As far as simplification is concerned, it looks like we have a 2x squared minus a 4x squared. So that's going to end up giving me a negative 2x squared. So let me take this over here. We're running out of room a little bit here. So negative 2x squared. And then it looks like we have a positive 4x and a negative 4x that would cancel, but I still have this negative 50x. And then it looks like I have a negative 50 at the back. And then still over denominator squared. All right, and then from the top, you've got, looks like some factors that are common. So definitely we can pull out a 2, because the first term's negative, we're going to pull out a negative 2. So we'll have negative 2, and then that leaves us x squared plus 25x plus 25. And then all of that is over this bottom piece squared. All right, now at this point we want to look on the inside and see if that trinomial is going to factor or not. Well, we can tell by the numbers on that one that it doesn't factor. Okay, we can't find any factors of 25 that will add and subtract to 25. So that's not going to factor. The bottom technically does factor. Notice that there's an x squared and a 2x, so both of those share a factor of x. So what we could do on the denominator is this. So negative 2, and then the x squared plus the 25x plus the 25 stays. Now I'm going to put 2 steps together in one because I'm kind of running out of room here at the end of this page. So if you factor an x out of the denominator, then on the inside of here, it would be an x times an x plus 2. Notice that that's still squared, so here's how we can write it. We can write it as x times, and then x plus 2, close that, and then leave the square there on the outside. So that would be an okay way to write the denominator. And then on this one, that would be our final answer. All right, I know the quotient rule is kind of a more difficult type of question. The product rule is too to some extent, but if you have any questions, y'all make sure to let me know.